Good morning. Detecting damage in engineering infrastructure is a critical issue, and this task of damage detection is often performed by periodic inspection. So, what happens in the periodic inspection? An engineer goes to the site and he looks the infrastructure for any kind of damage initiation. And if he finds any kind of damage, subsequently he plans for maintenance or repair action. Thanks to the sensor technology, nowadays basically we can deploy a sensor and we can collect the data, and this can be used to maintain or repair the critical civil engineering or any other engineering infrastructure. But the question is, do we detect all the damage using such kind of sensor? Or other way, what is the probability that a damage of given length cannot be detected using such kind of sensor? To answer these problems, we need a Bayesian method. So in this video, we will discuss how the Bayesian method can help to detect a damage or to give or estimate a probability of any damage length, whether it will be detected or it will not be detected. So here I have two pictures. One shows for building. So build often gets damaged. So often you find crack inside the build. So build maintenance or detecting the damage in the build is very important part. Another example is concrete. So if you see concrete, basically concrete also has many cracks that propagates either on the surface or inside the beams or inside the columns. So those cracks needs to be basically before the time those cracks should be maintained or should be repaired. Otherwise it will lead to a catastrophic failure of the beam itself. So we can use this is a rebound hammer test, and this is a non-destructive testing of the building. So that will basically give me the build length. So if you see a build, basically it starts a crack starts in the build, and the crack length is an important parameter. So what is the flaw length? What is the crack length? That is a important parameter. So flaw size, or we can say crack length inside the build, that is an important parameter that we can monitor, and subsequently basically we can avoid any kind of failure of the total structure. So depth of build defect, that is flaw size, is a random variable. So if you have large number of build connection in a structure, you will find each build defect, that is the crack length, is different. So we can assume that the crack length x is a random variable. So this is a random variable. The probability of detecting a flaw, so this is detecting a flaw, generally increases with the flaw size and detection power of the device. So there are two things that is important. So if I want to detect a damage, detect a crack, then of course if my crack size increases, I can detect the crack in a better way. That is, the probability of detecting a crack with increased size is more. And often if the sensor is having high sensitivity, in that case we will also able to detect. That is detection power. So there are two things that is important. What is my crack size? And the second point, what is my detection power? That is the sensitivity of the sensor. So this is detection power. So these 2 points are important for detecting any crack or flaw of a given size. So basically for any instrument, any given instrument, we can make a plot or we can make a curve that is called detectability curve. So for example, if I am using a sensor to detect the crack inside the belt, we can make something like this, a detectability curve. So this is a detectability curve. On the x-axis we have flaw size or the crack length. On the y-axis we will have corresponding probability. So let's say in this case we have something of this kind of curve. So this curve is coming from some measurement points. So we'll discuss this. So this is 0, this is 0.04, this is 0.08, and let's say this point is 0.12, and then finally I have 0.16, and this number is 1. So you see what this curve is telling us, that is flaw size. If I have a flaw of 0.16 inch, let's say we have inch on the x-axis, then I can detect this flaw with a probability of 1. And if I have a flaw of length 0.04, I can detect this with a very small probability, and that's just obvious. So if my flaw size is small, I can detect with a smaller probability. So this is a detectability curve, and that will depends upon my instrument. My instrument is sensitive, then I can have a different curve. So depending upon the instrument or sensor, we can have different kind of detectability curve. So this is detectability curve. So now if you see this graph, one important point, if we have a very small size crack, there is very small probability of detecting. This means I cannot detect all the flaw or all the defect inside a crack. So there will be some crack that is left and that has been not detected by the sensor. So hence, even when a structure is inspected and all the detected flaws are repaired, it is difficult to ensure that there are no flaws larger than the some specified size. So what we are saying is, even if you are basically done this inspection process using the sensor, but you are not sure that you have already detected all the flaws, because your measurement or your sensor is not so sensitive. So there will be some crack that is left inside this structure, and that will basically decrease the lifespan of the structure. So there are some cracks of a given length that has not been detected. Now let us use Bayesian methodology. So let's say this Px, this denotes the prior probability of crack size or flaw length of x, crack size of x length. This can be inch, meter, whatever the unit we have. And P d given x, this denotes probability of detecting a given crack size of length x. So this is what this is, probability of detecting a crack size. So basically I have been given a crack size of length x. What is the probability that it will be detected? So probability of detecting a crack of given size length x, given size x. We can also write complementary of this, that is PD var x, that is probability of not detecting a crack size of given length x. So this is probability of not detecting. So this point is important, not detecting a crack of given size. So this is given, conditioned, given size x. So this is basically my likelihood. And this is my prior. You see, the measurement point is given in this case. So data is given, and that's why this is likelihood. So data is given. Now we can write x given d bar. This is equals to probability of crack size x given it has not been detected. So these are the things that we have. So now we can use Bayes theorem. So if you see, so this is my posterior. So we can use Bayes theorem in this case, and then we can write posterior is equals to k times likelihood, and likelihood is this times prior. So if I know this term and this term, we can calculate posterior distribution of not detecting a flaw of given size x. So this is important part. So basically what this is saying, what is the probability of probability that a flaw size, given that it has been not detected, so what is the corresponding probability for a given size length x? So let's discuss this in more detail using a problem. We can also write this equation in terms of basically probability density function. So we can write fx d bar is equals to k times, and let us put this as in terms of probability, and this is f. So this is probability density function for the posterior, and this is the PDF of prior. So this is PDF of prior, and this is PDF of posterior. So let us illustrate all this using an example. Suppose that this is the problem for the belt size, belt defect. The initial prior distribution of the flaw size of depth x in a series of belt has a triangular shape and described y as follows. So basically we have tested a large number of belts defects, and we found that a triangular distribution follows for the belt, and we can write in mathematical form. So this is the prior distribution, PDF for prior. So this is equals to 208.3x when x lies 0 to 0.06, and 20 minus 125x when x lies between, so this is 0.06 and 0.16, and this is 0 when x is greater than 0.16. So this is what we have for the prior distribution. Now let us assume we are using some non-destructive testing, that is we are using some sensor to detect the damage or to detect the crack size, crack length, and that has a detection curve that we already showed. So we have detection curve something like that we have been shown earlier. So this kind of curve we have. So this is the detection curve, and we can write a mathematical equation for this curve. So the corresponding mathematical equation we have, that is PD given x is equals to 0 when x is less than 0 and when x is 0 to 2.125, this is at x, and this is equals to 1 when x is greater than 0.125. So we can also calculate the probability of corresponding complementary event, that is 1 minus p dx, and that is nothing but 0. 1 minus 0 is 1. So this is 1 when x is less than 0, 1 minus at x when x lies between 0 to 0.125, and 1 minus 1 is 0 when x is greater than 0.125. So this is we have for detectability curve. Now we can calculate posterior distribution, that is px given d bar, and this we have to basically multiply this term and the previous term, that is this function. So for this we have k times fx times p d bar given x. So this is k times. Now fx we have first is 0 to 0.06, so x lies between 0 to 0.06, and in this case we will have k multiplied by 208.3 into x times this term, and this term is nothing but when we have this is 1 minus at x. This will go up to 0.125. So this is second term I will have, this is when my x lies between 0.06 and to 0.125, this term will remain same, 1 minus at x, and 0.06 to 0.125, that is 20 minus 125. So this is k times 20 minus 125x. And when x is greater than 0.125, in that case this term is 0. So if I multiply, so it will become 0. So this is the function we have for the posterior probability density. So we can basically plot this function also, and we can also calculate normalization constant k. So if you remember in the previous classes we said how to calculate normalization constant. Basically this is this term is nothing but likelihood times prior. So if I sum all the likelihood times prior, and if I take inverse of that, that will give me the corresponding k value. So k is what? This is nothing but, so this will be 20, so this term and this term, so 208.3 into x, 1 minus at x plus 20 minus 125x into 1 minus at x, and this will I have to integrate. We will have different limit, so let's put different limit in this case. This will go 0 to 0.06, and this will go from 0.06 to 0.125. So if I do this integration, basically you will find, so I have performed this integration, and then if you do this, this term will come 0.4204, and now if you take inverse of this, this will give you the k value, that is 2.37. So now I know my normalization constant. So this is nothing but normalization constant that we also discussed in the previous classes. So this is normalization constant. Now let us plug this normalization constant, and we can rewrite the corresponding posterior distribution, that is this term, that is basically I have written this equation in terms of PDF. So this will be f, and this will also be f, and this was probability. So this was the corresponding posterior distribution. So now if I put the value for k, then I can rewrite this thing, and I can also rewrite this thing. So let us plug the value of k, and then we can write the expression for corresponding posterior distribution. So fx is equals to, so this is posterior distribution of fx, given that this has not been detected. So this will be 495x minus 3964, and when x lies between 0 to 0.06. And then 47.6 minus 678x plus 2379x square when x lies between 0.06, 0.06 and less than 0.125. And this is 0 when x is greater than 0.125. Now we can plot this prior distribution, posterior distribution, and the likelihood function. So we'll use Excel sheet to perform this graph. So we'll plot this and we'll see how this looks like. So there is a term of x squared that is missing. So let us plot in the x squared. Let us plot in the Excel sheet. So let's take a interval of 0.005. So we are having x equals to 0, then 0.005, 0.01. So this is the x. Now correspondingly PDF for the prior distribution, that is fx, that is given. So if you remember, this term is given here. So that is fx is given 208.3x, and then this is given. So we can plot this. So 208.3 times x. So this term is, so if you see here, this term is nothing but 208 point cell number A2, that is x. And now this will go up to x equals to 0.06, and then I have to change my function 20 minus 125x. So after this I have to change my function. So this function will become, now this function will be 20 minus, so let me show you. So this function is 20 minus 125 times a15, that is x. So now we calculated fx, that is prior distribution. Now we can calculate probability of d bar given x, that is the likelihood. So if you see here, we have this function, that is d bar given x. So this function is the likelihood. When x is less than 0, we have 1, and then we have 1 minus 8x. So basically we plotted here. So this function is 1 minus 8x, and then I also multiplied by a number 13.58. Basically why we do this, we will, so let's say for the timing, let's say I'm not multiplying this. So I am simply having this number, and this will go to all the points. So this will go for less than 0.125. So this number is 0.125 is here, and then all this will be 0. Similarly, I can also plot corresponding posterior distribution. That is, I have the function. In this case, the function is this when less than 0.06, and when greater than 0.06 I have different function. So I plotted this here. So this is corresponding posterior distribution 495 times A2, that is my x, 3964 times x square. So this is the posterior distribution, and when we have that is greater than 0.06 I have to change my function. So if you see here, I have 47.6 minus 678, and that is the same function we have here. So now we have plotted this graph here. So this graph for basically likelihood, and this is for prior. We already said this is a triangular prior, and this is the posterior distribution for a given length that has not been detected. So basically, to scale up this likelihood function, because this is a PDF, so we can scale up so that all things remains looks like in exaggerated way. That's why I multiplied by a number 13.48. So that is not required here. We can see whatever the likelihood prior and posterior distribution we have. So you see, initially if you see this prior distribution, so this is my prior and this is my posterior. So now posterior distribution is saying, now I can detect lower crack size also with higher probability. So you see the prior distribution probability is this much only, but now probability has increased. So basically this data is giving me, so the function of prior basically increasing the probability of detecting the flaw with a smaller size. Of course, if you have different prior distribution, then in that case your posterior will shift maybe right side, it may shift left side depending upon the prior distribution. So basically the likelihood function, this function is behaving as a filter, and that changes the posterior nature of the posterior distribution. So this is what we have in this lecture or in this video. So to summarize what we said, Bayesian method is an important method that can basically update the information that is coming from the sensor to achieve a task, whether a given damage has been detected or not. What is the probability that a given length has not been detected, or so such kind of question can be answered using Bayesian technique by applying or integrating the non-destructive testing data. So this is one application of Bayesian method that is widely used in engineering industry. So this you can also apply for other data sets also, other engineering applications also, where you have the data and you have some prior information. You can basically in that case modify the posterior distribution, and you can have some information for maintenance as well as repair action, rehabilitation of bridges, buildings, that can be done in a Bayesian manner. So we can stop here and then we can discuss something more in the next class.